Well, welcome our Space Science Classic to the third attempt at a video lecture. Hopefully these are going well for you. Today it's going to be chemistry and minerals. Now, usually at this point when we talk about anything to do with chemistry, I get sort of hot or cold responses. Either people loved what they have had in chemistry in the past for coursework, or they've not liked it at all well. Oftentimes it revolves around a poor teacher, and so or the belief that they're somehow genetically not able to do chemistry or understand chemistry, and that's not the case. So we're just going to take that small subset of chemistry today that pertains to geology, and we're going to look at it. Let's start off with some of the minerals aspect of things. Here on the picture, you see the world's biggest single gold nugget. This one on the right here is a model. Here it is on the left when it was originally found in 1869. 192 pounds of solid gold. Just imagine that. Love to find that. So if we scroll down a little bit, more recently, this one was found in 1980 in Australia. Evidently, Australia is the place to go to look for big gold nuggets. This guy was just moving around with a metal detector, and he found this thing a foot below the surface. Now, this guy right here is a little too fascinated by it. He worries me a little bit. Anyway, this guy found it in 1980, and you can go see this one. It was purchased by the Gold Nugget Casino in Las Vegas for, I think it was $1 million. Made this gentleman rich. I hope he knows this lady here. You know, maybe he's married to her, hopefully. But anyway, that's you know, some minerals that people have found in history and are of interest to people, obviously, because of their value. Another one that we could look at is the largest single crystal of emerald. This is over 3 feet long, if I remember right. Yeah, it says that. And weighed 752 pounds, the whole mass. Valued at over $400 million, this whole thing is, if you can imagine that. This actually was, I know it's got a mysterious history to it. It was found, they almost lost it in Hurricane Katrina in New Orleans, ended up in New Orleans in a warehouse. This person sued that person, sued the other person, and finally, now I guess it's in California, if I'm thinking right, and its ownership has been decided, but it was sort of murky for a lot of years. And then lastly, the largest diamond ever found. This was the Cullinan diamond. Oftentimes when you think of diamonds, I'll ask the class, are diamonds heavy or are they light? And oftentimes people will say heavy, and that's typically because you think of them in that gold ring setting that we oftentimes see them in. In actuality, it's the gold that's heavy. The diamond itself is quite light. This one weighed 1.5 pounds, and it was cut into 9 major diamonds. Right here is what it was cut into. Can you imagine wearing a 1.5 pound diamond ring? And it's just, even these are large. Here's Queen Elizabeth sporting one, so you know how big it is right here. Okay, the Cullinan diamonds. So that was early 1900s, and they were found in South Africa. So humanity has had an interest in diamonds and gold and emeralds and things of that for lots of years. And so looking at the notes then, we're thinking about the atoms that make up those minerals. And well, to keep the chemists happy, I have a description here. An atom is the smallest fraction of an element that can exist and still show the characteristics of the element and is not divisible by chemical means. It means you can't cut it up with a chemical knife. It's the smallest piece of matter that can still be used or can still do the things that that piece of matter does. Oftentimes we'll hold up a piece of copper from the Upper Peninsula of Michigan and ask what copper is used for. And people will correctly say it's used for wiring, and it's used for plumbing, and it's used in pennies, although there's very little in pennies anymore. We'll talk about why it's good for wiring. But as far as plumbing goes, it's because it's malleable and easily bendable, shapeable, if you will, and you can solder it. But there's another thing that copper is good for in plumbing, and that is that it has antibiotic capabilities. Bacteria don't grow well on copper, so it's good to have our water supply being delivered in copper lines to help protect us from bacterial contamination. So that would be an example of a characteristic that something like copper would have, for instance. And there are many other characteristics. So then if I asked you what an atom would look like, you would probably come up with some image similar to this. Now, if you've had chemistry in the past, which I assume you all have, you might well, maybe you haven't, but you might well pick out some problems with this diagram, such as the electrons, which are here, are the same size, relatively speaking, as the protons and neutrons, which are found here in the nucleus. In actuality, the electrons would be much smaller. They're about 1/1850th of the size of the protons and neutrons. Another issue is that the electrons are way too close here to the nucleus of this atom to really be represented accurately. In reality, if you take this model and we go to a place like Target Field, where the Twins play downtown Minneapolis, and if you take that atom and if you were to expand its nucleus so that it was about the size of a gumball and put it out here behind second base, the electrons would be, relatively speaking, the size of specks of dust whipping around the nosebleed seats way up here. Okay, so that this image of the atom doesn't give you an accurate impression of the amount of space between the nucleus and the electrons. And that's going to become pertinent also when we get to astronomy. So the parts of the atom, now there's lots of parts of the atom that aren't shown here. We've got protons and neutrons in the nucleus and electrons surrounding the nucleus. But in reality, there are positrons, quarks, neutrinos, muons, taus, all these other subatomic particles that are important to physicists, but aren't really something we're going to worry about in geology. We're going to stick with the big three: electrons, protons, and neutrons. Proton, if you look at your notes, has a weight of 1 and a plus charge. Well, 1 what, you might ask? Well, it's 1 AMU, or atomic mass unit. You can imagine, it's possible now that the very largest atom could be viewed in some form under a microscope, but for the most part, we can't even take the best microscope we've got and look so closely at something that we can see an atom. They're just too small. And so a part of an atom would be even smaller. How do you weigh that? Well, if we were to weigh it in grams, it would be such a huge decimal number, 0.0000, bunch of zeros, and then some other number at the end of it, that it would just simply be too large. And so chemists came up with an AMU, an atomic mass unit. It's got a weight. It's 1/12 the weight of a carbon atom, but to come up with, so there is a gram weight for it, but we just call the weight of a proton 1 AMU, 1 atomic mass unit. The weight of a neutron, 1 AMU. Just to give you an idea, an electron is 1/1850th of an AMU. So it's way smaller than a proton or neutron, but, as we're going to find out, its charge, the charge of an electron, is equal but opposite the charge of a proton. Of course, a neutron doesn't have a charge. Okay? So, when it comes to putting these together, you may be used to, something like atoms combine to form molecules, which combine to form compounds. You might even throw combine to form mixtures in there. But in geology, we're going to approach this a little bit differently. We're going to talk about atoms or elements, which combine to form molecules, which then combine to form minerals, which then combine to form rocks. So that's the progression we're going to be interested in. We've already talked about the next term in your notes, and that is an isotope. I held up that cow bone, and we talked about how would you age it, and we talked about most carbon atoms in the world have 12 protons and 12 neutrons. So if we look here at this periodic table, and I'm going to blow it up just a little bit. So if we look here at carbon, this number right here is the atomic number, and that is the number of protons that the carbon atom has. Boron has 5, carbon has 6, nitrogen is 7, oxygen is 8, fluorine 9, so on and so forth. That's how many protons are there. For most of the smaller atoms we are going to be worried about, you can assume that the number of neutrons is going to be very close to that, or the same. And so down here, we see under the word carbon, we see the atomic mass. That is the number of protons plus the number of neutrons. So if we've got 6 protons, there must also be 6 neutrons to get to 12. But notice it's 12.011. Well, if you remember, when we talked about radiometrically dating something, carbon dating something, I talked about most all the carbon in all the world has 12 protons and 12 neutrons. That's true. Every now and then you find a carbon atom with an additional neutron, making it carbon-13, 6 protons, 7 neutrons, but that's stable, doesn't break down. Even more rarely, you find a carbon atom with 2 additional neutrons. So that would be 6 protons, 8 neutrons, and that's carbon-14. So this number right here, 12.011, is an average of all the carbon atoms in all the world. Almost all of them are carbon-12, but a few are carbon-13, a few are carbon-14, and that gives us a number slightly bigger than 12, and so that's what we have an atomic mass of 12.011 for carbon, to account for the isotopes of carbon, like carbon-14. Those carbon atoms with more neutrons than most all the other carbon atoms in the world, an isotope. When it comes to the electrons, then, yeah, there's lots of ways to characterize this, to represent this, but I'm going to use a particular format that I think works well. And so we know then that given this model with all its imperfections, we have a nucleus which is made up of, for our purposes, protons and neutrons, and then electrons around it. How do those electrons exist then? Well, if we consider how they exist, here's that carbon atom again. We find, at least for the small atoms we're worried about, there's a specific arrangement. So here's our nucleus with protons and neutrons, and here are the electrons that are circling that nucleus. Now, we are talking about shells here, kind of think about layers. Orbitals is another term used to describe them. In the first shell out from the nucleus, we have 2 electrons. Now this shows them occupying or moving in a very nice circular path around the nucleus. In reality, it's probably a good bit more erratic than that, but it would be somewhere inside of this path. So the first shell out from the nucleus, there are 2 electrons, or an atom wants to have 2 electrons. In the second shell out, an atom wants to have 8 electrons. Now this one, this carbon atom, only has 4. Okay. And so that is called the octet rule, this arrangement of atoms. And the next one out, again, the third one would want, again, to have 8 electrons in it. Now, we're not talking about p orbitals and s orbitals and organic chemistry of that sort. We're just worried about the little bit of chemistry pertinent to geology. And so for our purposes, 2 in the first shell, 8 in the second, 8 in the third, that's what atoms want, but they don't all have it. So if we go back to this diagram right here, when we look at the periodic table, and I'll blow it up again a bit, and we looked at carbon, okay, and so right here, if you see a 6 telling us the number of protons, and there's no plus or minus right about here by the letter representing the element, in this case carbon, then you can assume that there are 6 electrons in that as well. Okay, so 6 protons, no plus or minus, tells you there's 6 electrons. If there were a plus sign here, that would indicate there are more protons than electrons. So if it was a plus, it would be 6 protons, 5 electrons. If there were a plus 2, 6 protons, 4 electrons. If there were a minus 1, 6 protons, 7 electrons. That's how that would work. So if we go back here, then we see that for carbon, 2 electrons in the first shell, it's only got 4 in the second shell. That second shell is not filled. That's an unhappy atom. Okay? And so if we look at then an element like hydrogen, over here, let's see here. Can't even get there. Okay. There we go. Way over here, hydrogen, we can see it has a 1 here, telling us there's 1 proton. It has 1 here telling us the atomic mass. Wait a second here, 1 proton and a 1 here, which means there's 1 proton, there's no neutron there. And then there's no plus or minus here, so that tells us the 1 proton, there must be 1 electron. All hydrogen is a proton with an electron around it. Very simple little atom. So it would only have 1 electron in that first shell. Helium, if you look at that, it has 2 protons and it has 2 neutrons, since there's a 4 here. No plus or minus means there are 2 electrons, and it has a filled outer shell. Neon here, there's 2, or there's a 10, no plus or minus, so we'll assume 10 electrons. So 2 in the first shell, 8 in the second. It's got a filled outer shell. Argon, 2, 8, and 8, filled outer shell. Krypton, xenon, radon, I don't know on. All the little humor there. All these have filled outer shells and are very stable because of that. That outer shell is also, you may have heard the term valence shell. The shell that has a lot of energy, and the electrons there are not so easily held by the nucleus, are more likely to be lost, and so they're the ones that can be lost to another atom, these out here, or shared with another atom. Yep, that's going to become important when we talk about the next thing, which is bonds. James Bond. Bonds, yeah. Did you guys see the new Bond movie? You guys tell me what you thought of it. We'll consider 3 types: ionic, covalent, and metallic. I suspect ionic and covalent are familiar to you. And so just a brief rehash, an ionic bond is a bond between 2 atoms of opposite charge. And so if we look at sodium here, here's a sodium atom, 2 in the first shell, 8 in the second shell. Look at that third shell only has 1 electron. So it will very commonly lose that single electron in its outer shell and then become an ion, an atom with a charge. Now this atom has more protons in the nucleus than electrons surrounding it. More protons, 1 more, equals more positive charges, so a plus sign appears right there. We have a sodium ion. Well, chlorine atom has, if you see here, 2, that's good, 8, that's good, and 7 in the outer shell, so it's only missing 1. So it's very logical that that outer electron in the sodium goes to the chlorine. When the chlorine picks it up, it becomes chloride, and you have a bond between sodium and chloride, and that forms table salt. Salt, which we're going to learn is called halite to a geologist. And this is a square pattern. This is very common for salt crystal to have that sort of a shape to it. Covalent bonds are formed when 2 atoms share. Now, in this case, this electron is lost. It no longer circles around this nucleus. It now circles around this nucleus. But in the case of a covalent bond, this electron is kind of spending time around 2 nuclei. It's shared between this nucleus and this nucleus in a carbon atom. If you remember, carbon atoms have 4 electrons in its outer shell. Now, so this carbon atom, since it has only 4, it wants to share 1 here with this carbon. There would be another carbon here, and another carbon here, and another carbon here. Each of them, this carbon atom would share an electron with 4 other carbons. And then, since that electron spends some of its time around both nuclei, it's happy. You know, honestly, this carbon atom could share 2 electrons with this carbon atom, and it would be a double bond then, because it's sharing 2. And so you'd only need 1 carbon atom here, 1 carbon atom on this side, and you would have a different arrangement of carbon atoms. And so when we look at that fact, you can see variability in how carbon bonds together. Sometimes it bonds together in a complicated 3-dimensional network and creates diamond. Sometimes it bonds in these sheets and it creates the mineral graphite. It's the same element, it's carbon in both cases, but they're bound together in slightly different arrangements, and usually that has to do with the environment in which they bond together. That can create that. Diamond has to form in a high pressure, high temperature environment. and graphite a little less so. In fact, if you squeeze and heat graphite, or coal, coal also has a lot of carbon in it, you can make a diamond. Okay? And so that's diamond. Covalent bond, shared electrons. The last bond is a metallic bond. And that's the one that I suspect is a little bit unique. In a metallic bond, there are shared electrons. So these are individual atoms, and those shared electrons are able to move all through this mass of metal and hold it together like a net. Okay? And when I think of this, I think of Finding Nemo, you know? When I think of when Dory and Nemo are caught in the net with the fish, you know, and here's all those fish in the net. This would be like a metallic bond, where those electrons moving freely and randomly through this whole thing create sort of a net around the mineral and hold it together. Might be going a little far, but that's works for me. Hope it works for you. Okay, so that's a metallic bond. And because those electrons are free to move through that whole mass of mineral, that makes metals typically good conductors of electricity. To conduct electricity means electrons are moving through the mass of mineral or whatever, or the wire, which is made of a metal. Okay, states of matter. There are 4 states of matter: a solid, a liquid, a gas, and a plasma. And this is an attempt to represent the mineral, the atoms, the arrangement of atoms in each of those types of matter. In a solid, the atoms are closely packed together, not much movement. In a liquid, they're more dispersed and capable of movement, and so liquids obviously can pour. In a gas, they're even more dispersed and move easily. And then in plasma, you have extreme movements and ionization. Sometimes you have just electrons floating around in high energy environment. And lightning is a good example for that. We'll talk more about that when we get to astronomy. But since we're talking about states of matter, that's a good place to start. You will also see the term organic and inorganic, and simply all we're going to say about that is organic means that the substance contains carbon, and inorganic means it does not contain carbon. So then if we jump to minerals, and if we think about minerals, again we'll go back to diamonds. This is the Hope diamond. Notice it's blue in color. It's on display at the Smithsonian. And diamonds are weighed, if you will, and compared in carats. Now, a carat is a misnomer. It's actually a carob. This is a carob tree, typically an African species. It has bean pods like our locust trees do. And that's actually a carob seed. This is what it looks like in a person's hand. They're light seeds. And so 1 carob is supposed to be equivalent to a 1 carat diamond. A 1 carat diamond is a pretty good sized diamond. Remember the Cullinan diamond. This one right here, over 3,000 carats. Yeah, that's pretty substantial. Okay, so a mineral, then, the definition, is a naturally occurring inorganic solid with specific crystalline structure, chemical composition, and physical properties. So does that mean that diamond is not a mineral? Because diamond contains carbon, but I just described a mineral as inorganic. It doesn't. This diamond is an exception to the rule. One of the things you're going to discover when we talk about minerals and rocks is we'll try to characterize and classify them, but there are so many exceptions to the rule that it can be a little problematic sometimes. Well, here's the first one. Diamond does have carbon. It is still a mineral, but for the most part, minerals don't contain carbon. Minerals are always electrically neutral, so if you pick one up, you won't get a shock. Minerals are composed of a single type of element, but usually contain 2 or more. So, for instance, these gold nuggets that I showed you before contain mainly gold, Au, and that's good. But more commonly, minerals contain multiple types of atoms. If you were to take all of Earth's crust and break it up into the atoms that make it up, or the elements that make it up, you'll find 8 make up 98% of Earth's crust. They're listed there in your notes. I suspect some of them might be logical, and others you might be surprised at. Like number 1 there. I would guess oxygen would not be first on your list. Silicon is number 2 on the list. So those are the 2 most common. And then we have aluminum, iron is Fe, Ca is calcium, Mg is magnesium, K is potassium, and Na is sodium. Na, natrium is Latin for sodium, hence the Na. Ferric or ferrous is iron. That's what gives iron its Fe. So of that list, then, I'll pull that list up here. Of that list, then, it is silicon and oxygen that are most common. I was just pulling up this. Isn't that a cool picture? That's an actual picture of a ruby. Just a beautiful mineral. Okay, so silicon and oxygen are most common, so we want to pay attention to them. Minerals that contain silicon and oxygen are called silicate minerals. And those minerals make up almost all of Earth's crust, so we better pay attention to them. When we look at silicon and oxygen, they bond together in very specific ways. Here are 3 different ways of portraying how silicon and oxygen bond or react with one another. Always you have that little silicon atom in the middle and the larger oxygen atoms, 4 of them around it. Tetra, 4, okay? And so that's the silicon-oxygen tetrahedron that silicon and oxygen form. Okay, so now when you have this as your basic building block, if you look at a brick wall or a concrete block wall, the concrete blocks or the bricks would be the building blocks. Well, if you pick up a mineral of any sort, this is the basic building block of most minerals. Now, not gold, of course, because that contains gold, but most of the minerals you pick up on Earth's surface are going to have this as the basic building block. So one of these, however you wish to think of them, is connected to another, and makes the mineral that you have. There's 5 ways that these typically bond together, and they're represented down here. So here's a single silica tetrahedron, and when one of these is bound together to another one with a metal atom in between, you get a particular kind of mineral, and a good example of that would be olivine. Now, olivine has got one tetrahedra bound to a magnesium ion, to another tetrahedra, another magnesium ion, another tetrahedra, and you get this greenish mineral. That's the way I remember it. Olivine is olive green. Well, if you take the tetrahedra and bond them together to make single chains like we're seeing here, then we're going to get another kind of a mineral called pyroxene. Looks like a dark rock. Well, we're not going to have to know what pyroxene is, but that's what's inside of this. It's long single chains of tetrahedra bound together. Okay, sometimes those chains are doubled, and we get a double chain. And we're going to look at a mineral. I'm going to want you to know this one, because it looks so much like pyroxene. This is called hornblende. And this is a black mineral, and inside it there are long chains, and we're going to see that it has a specific crystal structure that helps us identify it. Sometimes those tetrahedra are bound together in sheets. So here you have a chain, multiple chains, and you get a mineral that is made of sheets like this mica here. Could you picture up a picture of pulling off a thin sheet of this? It's a very soft mineral, and you can kind of get an idea that there are sheets of it, thin, flat little sheets. Each of those sheets is made of tetrahedra that are bound together like I was talking about. And then sometimes you get tetrahedra bound together and they make a complex 3-dimensional network. And a good example of that is going to be the mineral potassium feldspar. Feldspar is a term you'll become familiar with. It's a very common mineral, although I would suspect very few of you have heard of that word feldspar. You have probably heard of quartz. There's a quartz crystal. Those are made of silica tetrahedra bound together in complex ways. Now, as I mentioned, there are also important non-silicate minerals like halite or salt, carbonates like The calcite-like cement contains a carbonate concrete. And then the metals like copper, gold, platinum, silver, all those are non-silicate minerals. They are important, but they don't make up that much of Earth's crust. Went a little long with this one. I apologize, folks. And I'll see you in lecture on Tuesday. Thank you.